Okay, so let's think about conditional probability. The probability of an event often varies depending on the occurrence of one or more related events. For example, the probability of rain on any given day may be approximated by taking the ratio of days that it rains within a month over the total number of days in the month. Now suppose, though, that we wish to consider the probability of rain tomorrow, given that it has rained continuously for the past 2 days. Certainly, this probability differs from the former one. This probability depends on the fact that it's rained for the past 2 days. In other words, this probability is conditional on another event. So conditional probability, the conditional probability of an event A, given that an event B has occurred, is equal to the probability of A intersect B over the probability of B, as long as the probability of B is greater than 0. Okay, so suppose that a friend rolls a 6-sided die and asks you to guess what number came up. If you guess a 1 and your friend tells you that an odd number was rolled, then what was the probability that your guess is correct? Okay, so let's just think our way through this. Let's define A as the event that we roll a 1. And let's let B be the event of an odd number, rolling an odd number. Then what it is that we're looking for here is we're looking to find the probability of A given B. We want the probability that we rolled a 1 given that what was rolled was an odd number. And we know that this is equal to the probability of A intersect B over the probability of B. Okay, so now let's think here about this. Probability of B, we could probably figure this out pretty easily. Probability of B is getting an odd number. And we know that with a standard 6-sided die, there are 3 odd numbers. And so let's just go ahead and write that down. The probability of B, there are 3 odd numbers out of 6. And so we can see that this is just going to be 1/2. Now let's think about the event A intersect B here. Okay, so this would be the event we roll a 1 and that we roll an odd number. Well, it just so happens that 1 is an odd number. And so this really is just the same as event A. And so the probability of A intersect B is just going to be the same as the probability of A, which is getting a 1 when we have 6 possible choices for what we could roll, which is 1/6. And so our conditional probability over here is going to be the probability of A intersect B, which is 1/6, over the probability of B, which is 1/2. And we see that this ends up giving us a probability of 1/3. Okay, so 2 events are said to be independent if the probability of the intersection of A and B is equal to the probability of A times the probability of B. Note that this implies that the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B. So example, consider the following events in the toss of a single die. Event A is that we observe an odd number. Event B is that we observe an even number. And event C is that we observe a 1 or a 2. Are the events A and B independent? What about events A and C? Okay, so let's think about A and B. A is the event that we observe an odd number, and B is the event that we observe an even number. Now, A and B can't both happen in the toss of a single die. So we know that the probability of A intersect B is 0. Now, we can also say that the probability of A getting an odd number, there are 3 odd numbers, 1, 3, and 5, out of the toss of a single 6-sided die. That probability would be 3 out of 6, which is 1/2. And that's the same thing as the probability of B. There are 3 even numbers out of 6, and so that's also 1/2. And so we can see here that the probability of A intersect B is not equal to the probability of A times the probability of B. This is equal to 0 on the left-hand side, and we have 1/2 times 1/2 here. This is not equal, which means that A and B are not independent. So let's think about A and C. So A intersect C. Well, A is the event that we observe an odd number, and C is the event that we observe a 1 or a 2. And so we can see that the intersection of these two things would be that we observe a 1. And so the probability of A intersect C, all right, is, there's only 1 out of 6, and so that gives us 1/6. Now let's think here about the probability of A. We've already seen that equals 1/2. And the probability of C, so there are 2 sample points in our event C, and so that gives us 2 out of 6, which is 1/3. And we can see from this that the probability of A intersect C is equal to the probability of A times the probability of C. That is, we have 1/6, which is equal to 1/2 times 1/3, and that's a true statement, which tells us that A and C are independent. Okay, so let's think about some other laws of probability. The following laws demonstrate how to find probabilities of unions and intersections of events. Since we know that the probability of A given B is the probability of A intersect B over the probability of B, it follows that the probability of A intersect B is equal to the probability of B times the probability of A given B, which may also be written as the probability of A intersect B equals the probability of A times the probability of B given A. That's done just by interchanging A and B. And if A and B are independent, then what we know is that the probability of A intersect B is equal to the probability of A times the probability of B, just like we've seen before. So for example, among those who apply for a job, the probability of being granted an interview is 0.1. And among those interviewed, the probability of being offered a job is 0.25. So we want to know, what is the probability that an applicant is offered a job? Okay, so let's label these things. Let's say A is the event that an applicant is granted an interview. Okay, so granted an interview. Okay, and so let's think about B. Let's say that B is the event that an interviewee is offered a job. Interviewee is offered a job. So the probability that I'm really trying to find is the event A intersect B. That is, that someone is granted an interview and that interviewee is then offered the job. This is the probability that I want. But let's think about this second event right here. This event really can't happen unless the first one has happened. So this is not really just event B. This is event B given that A has happened. And we know here that the probability of A is 0.1, the probability that an applicant is granted an interview. And we're told that the probability that someone who has been granted an interview is offered the job is equal to 0.25. And so the probability that an applicant is offered a job, this probability right here, is the probability of A happening times the probability of B given A. And we have 0.1 times 0.25. It looks like the probability that an applicant is offered a job is 0.025. So let's talk about the additive law of probability. The probability of the union of two events, A and B, is the probability of A plus the probability of B minus the probability of the intersection of those events. And if those events are mutually exclusive, then the intersection of those events will have a probability of 0. So we can simplify our additive law of probability here. Okay, so let's look at an example. Disease 1 and 2 are prevalent among people in a certain population. It's assumed that 10% of the population will contract disease 1 sometime during their lifetime. 15% will contract disease 2, and 3% will contract both diseases. Find the probability that a randomly chosen person from this population will contract at least one disease. What if contracting one of the diseases provides immunity against the other? What's the probability that a randomly chosen person will contract at least one disease in that case? Okay, so let's define event A to be the event that someone contracts disease 1. And event B will be that someone contracts disease 2. Well, then we can infer from the problem up here, 10% of the population will contract disease 1, so we can see that probability of A is 0.10, and 15% will contract disease 2, so probability of B is 0.15. Now we are also told that 3% will contract both diseases. So that would be the event A intersect B, both diseases. And we can see here that the probability of A intersect B is equal to 0.03. So this is the probability of both diseases. So we want to find the probability that a randomly chosen person from this population contracts at least one disease. At least one disease. That means they either get A, or they get B, or they get both of them. That would be the probability of A union B, which we know from our law that probability that equals the probability of A plus the probability of B minus the probability of A intersect B. So we have 0.10 plus 0.15 minus 0.03, which equals 0.22. Well, what if contracting one of the diseases provides immunity against the other? Let's think about what that means. So under the case where we get immunity, if one of the diseases provides immunity against the other, what that means is then that that A intersect B is the probability of this is going to be 0. Because you can't get both diseases in that case. And if that's the case, then we have the probability of A union B is equal to the probability of A plus the probability of B. And since and that would be minus the probability of A intersect B, but in this case, these are mutually exclusive. So the probability of A intersect B is equal to 0, which means we have 0.10 plus 0.15 minus 0. The probability of getting at least one disease would be 0.25. Okay, and then we get our last law, which is that if A is an event, then the probability of A is equal to 1 minus the probability of the complementary event. Or we can write that as the probability of the complementary event equals 1 minus the probability of A.